Hello everyone, this is NAQVI from Similar Research Lab in Norway. Today I'm going to present my paper which is titled on evaluating self-adaptive and self-healing systems using chaos engineering. First of all, I will present why this study was needed. So, as many papers have mentioned, there is a lack of systematic evaluations in self-healing and self-adaptive systems. Secondly, most of the evaluations that have already been done are based on some sort of models of these systems, which may not be able to capture runtime executions of the systems. Moreover, there can be black box components within managing systems, which can make it even harder to evaluate the systems. And most of these self-adaptive and self-healing systems have different types of adaptation strategy, which can change the way evaluation can be done. And last but not least, because these systems are reactive and they show different types of behaviors at runtime, we need evaluation strategies that can help show these emergent behaviors in the system, which might not be available at the design time. So for making up this evaluation, we started with what we call a MAPK loop. You can see on the top side of this figure, a self-healing system with a managed system, which is extended using this, which is called MAPK feedback loop. And we added a couple of components along with this MAPK loop. And these components include system self-monitoring and fault injection. We argue that adding the system self-monitoring and fault injection can help in making an evaluation. Furthermore, this is the high-level process flow in our approach, which we have called chess. So we use the principles of chaos engineering to build this process. So first of all, in designing a chaos experiment, we build our hypothesis about the normal functionality of the system. We define steady states, and based on that, we develop a pool of experiments. And once we have these experiments, we choose some of these experiments and we use fault injection into the system. So once we have these fault injection, we can check the steady state of the system. And how we generally do that is by looking at system logs. And these system logs can be system executions. And along with these system logs and quality attributes and user requirements, we can evaluate the system. And this evaluation can further result in evaluation feedback, which further goes back to the input for designing further chaos experiments. So this whole process can run as a loop. Moreover, when we were examining our approach, we looked at this study from an angle of these three research questions. So first of all, we examined like how we can use the chaos engineering for the evaluation of self-adaptive and self-healing system under realistic failure scenarios. Secondly, we considered the observability of the system because different systems can have different observability and how this impacts the evaluation. And the third one was looking at some of the limitations of using the chaos engineering for evaluation. So there were several factors which we considered while designing our exploratory study. So first of all, we looked at the studies that have described or that have investigated commonly used quality attributes in these self-adaptive and self-healing systems. Secondly, we looked at how failure models are designed. And last but not least, we looked at different environments in which like this study can be done. So for commonly used attributes, we chose these four: availability, reliability, integrity, and performance. For failure models, we looked at some state-of-the-art studies, and we decided upon these factors to look into. And similarly, for the environment, we chose distributed systems based on microservices architecture. There are many benefits to that, and we can make a good case study using this kind of architecture. So this is the implemented form of our case study. So we used Kubernetes environment, and we made these services. And you can look at this architecture. It has different components. So when using this architecture, we thought of like how we can inject faults, or how we can like create different failure scenarios. And we came to the conclusion that we will use these 4 types of failure scenarios. So we can either turn down a running service, or we can add some erroneous readings into a deployed sensor. Similarly, we can turn off a running sensor. And last but not least, we can add delays to a running service. And these 4 further can be mapped to like different types of the quality attributes that we consider. So you can see like, for example, failure scenario 1 corresponds to availability, reliability, and performance, while failure scenario 4 is focusing on availability and performance. So we did 2 rounds of chaos experiments while we were examining different types of behaviors in the system, and looked at like how it impacts the quality attributes. So first round, we did what we call self-healing experiments, and we use failure injection and examined the blast radius into a single service or multi-service. And in round 2, we did self-adaptive experiments. So we looked at service requests, and we examined the performance of the system with a stepwise increase in the service requests. So for round 1, which we call as self-healing experiments, we examined the blast radius. So blast radius is looking at how much impact one failure can have. And this is very crucial in, let's say, microservices-based architecture, or different types of systems where like a single point of failure can impact the system. We did like 8 different types of failures into different services. So in the figure that you can see now, you can see different types of colors. And these can be explained as like the gray are the ones which are the services which we have targeted for one specific scenario, and green are like normal services. Yellow is the one that have a very low level impact, orange medium level impact, and the red one has the high level impact. So you can see like if when we inject the fault in the temperature sensor, it affects the user interface, but it also affects a heating control service. So heating control service is seriously damaged because it depends on the temperature sensor service. And once the temperature sensor service has an issue, it affects the heating control. And after a specific time, we can observe that heating control service failure leads to heating actuator service failure. So this is another type of like failure that we are interested in. So in for example, second type, you can see here that we injected the failure in motion sensor service, and it affected light control service. But since light control service depends on motion sensor service and external weather service, it has a medium level impact because it can still work based on like partial information. But this light control service then leads to the impact on light actuator service. And similarly, if you look at external weather service, that also affects partially light control service, and similarly light actuator service. And the fourth one, where you can see the MQTT broker service is impacted, and it damaged all the services. So you can look at the paper with like more examples. Due to shortage of time, I'm only showing you these 4 here. So moving on to the second round of experiments, which were self-adaptive experiments, we analyzed the performance of the system by gradually increasing the load. So we started adding 1 user every 20 seconds, and we also let the users attempt to access the light controller every second. So there is a gradual increase on the load. And so on the top of this graph, you can see like the increase on the number of users and the responses per second. And on the top in the green dots, you can see the number of replicas. So this self-adaptive systems manages this load by adding more replicas of the services to manage the response time. So in the bottom part, you can see blue line shows the average response. So in the average response, you can see like there isn't like much of an impact, but 1% or 10% of the users may experience a very low response rate. But one more thing that you can look at the graph is like once we have dropped this number of user in the top part, you can see that the number of replicas aren't decreased right away. So the self-adaptive service has waited for a specific time to see maybe if there are further load coming, but after a specific time, it has decreased and it went back to a single replica of service to manage the load. So what lessons we have learned through this study? So the first research question was how the chaos engineering can be leveraged to create realistic failure scenarios. So there are like two types of failures or faults. These two categories include infrastructure level and functional level faults. So infrastructure level faults can be managed by chaos engineering very well. Using the chaos engineering principle, we can easily inject faults with like on different infrastructures, but when it comes to functional level faults, we need more information. So if there is a black box component and we don't know much about the functionality within these components, then it can be harder. But using our approach, we added like different scenarios where you can see like what kind of faults is needed. So for example, for sensor fault or for sensor down, we need functional level faults, which can be done like implemented depending on the technology, but it needs a little more information. And that leads us to the second question, which was about observability. So observability is one of the important factors while we are performing evaluation on a system. So there are like a number of factors here. So the most important is the black box manner of the observability in containerized applications. If we have, if the components, we don't know the functionality inside the components, then it can be very challenging to perform the evaluation. But thanks to some monitoring tools like Prometheus, Kiali, and Grafana, we can have some extra information. Similarly, chaos logs can be used, which gives us information about exploited services, and when the system states change, we get these indicators in the chaos log. And one more thing that's very useful is system self-monitoring that allows us in-depth observability of different components within our system. So here you can see in this table that what kind of observability we need for a specific type of failure scenario. And moving further, we looked at like the limitations of chaos engineering for the evaluation, and one of the main challenges is this cascading effects of chaos experiments. So many of chaos engineering experiments can seriously disrupt the system. So it's important to know how to limit this blast radius. So these three factors are very important in this regard. So context awareness helps us know the context of the failures and how the system manages them. And secondly, the priority awareness, which means like how self-healing or self-adaptive system prioritize different types of faults. And thirdly, like conditional monitoring helps here. So if we have monitoring to very specific components, we can only focus on the failures on these types of like parts or components of the system, which helps us limit cascading effects of the chaos experiment. In summary, what we did is like we made a system using MAPK loop by adding fault injection and system self-monitoring. Then we developed this process flow which to do the evaluation, and we performed evaluation on this case study, and finally we discussed about the lessons learned in the paper. So you can look at the replication package of this study at this link, and this is my contact information. Thank you so much for listening to this presentation.